So what I can do now, I'm going to be sketchy. The idea is easy to grasp, but I'm not going to give them the details. You do it in a finer and finer way. Imagine that you take, let's say, delta equal 1/2. You do this construction with 1/2. Okay? Now, from the partition which is here and A1, A2, A3, A4, and there's a map T delta. Okay? Just asking that the measure of the new delta mass, which is here, is the same as the mu mass of the AI. It's just this condition here. But now the trick is to do it in a finer and finer way. Imagine you take delta equal 1/2. You do this job. Now you keep the partition you have done for delta equal 1/2. You take a finer partition. You take a finer partition here, but you also take a finer partition here. Okay, you do it this way. This way you define a sequence of maps, which you can prove to be Cauchy in L1. Okay, so it's going to converge. And okay, so you do it, you refine this construction. I take delta equals 1/2k, for instance, and each time you have done a correspondence between the partition on Y and the partition on X for 1/2k sets, at the next step, you take a partition with diameter here 1/2k plus 1, but you take a sub-partition here, you refine, and the next generation, you refine the partition here, the partition there, and likewise here, likewise there. Okay? And you said Tk equals T delta K, and you can prove that Tk converges to some T, because it is Cauchy in L1 of mu. Okay? And then the T does the job. And T, I'm skipping the details, I don't want to be too technical, but the idea is, you see, the only obstacle to build a transport map is the first step, the presence of atoms. If I measure at atoms, okay, maybe this condition is not true. Maybe there are values of alpha between 0 and 1, which are not taken by the measure. It's the only obstruction to construct a transport map. Okay? Okay. So if there is no atom, there is an abstract theorem which says there is a construction. It's quite complicated because you have to do by induction to pass to the limit, but it's a classical. Okay? Is it clear? Okay. Now, I'd like to do something else. Another way to consider transports is a dynamical viewpoint. So it's paragraph 2.3 because I started 2.1 was the monotone transport, 2.2 was the triangular transport in dimension 2 and it generalizes to higher dimensions. Now I like to have a dynamical viewpoint, transport of a measure by a flow. Okay. So dynamic viewpoint. What do I mean by this? So far, I have not talked about taking into account a time variable. Now, I want to introduce the time in the following way. So, I'm going to work in RD. I'm going to consider a domain in RD. Domain, smooth domain. Say bounded if you want. Domain. That's my omega. Could also work on the whole space, making some assumptions. But everything will happen in this region omega. And I'm going to consider a vector field. the time-dependent vector field. So there is a velocity field. So there will be a time horizon capital T. So vector field, which is time dependent, is the map V from 0 T times omega to RD. So it takes a time, it takes a position, it gives you V of Tx, which is the velocity at position x at time t. Okay, and I will also assume that somehow, if particles follow the flow of this vector field, they do not leave the region V. So you can convince yourself that a condition for, in fact, I'm interested in the flow of the vector field. So if V is like this, particles will follow the ordinary differential equation x dot equals V of x, V of t and x. But if you want that particles do not leave the region, you have to assume that V is tangential to the boundary. By this I mean that for every t, for every x in the boundary, the vector field is tangential, right? It's orthogonal. X is a point in the boundary. So this is n of x, the normal unit vector. And the vector field is directed, lives in the tangent space. So it means that this scalar product is zero. Okay? Of course, I could work also on the whole space, assuming that V has a certain behavior at infinity, but I don't want to get into this. And now I'm considering the flow of the vector field V. I'm assuming also that it is smooth. Okay? Smooth vector field. And I'm interested in the flow of V, which is the solution of the ODE, V of t, d over dt of x t of x equals V of t and x t of x, where the dependence with respect to x is that the flow starts at time 0 at x. Okay, so you have a particle which starts here at time 0, which is here, it follows this vector field, and then depending on the vector field, maybe do complicated things. So x is the position of a particle starting at x at time 0 is moving according to this dynamics, and V is given. Okay, is it clear? So it is well defined. The flow is a nice, both smooth and invertible. So you are in the framework where you can apply the Cauchy-Lipschitz standard theory. And here you are. Now the viewpoint is that you are not interested in one particle, in particular trajectory of the equation, but for a bunch of evolution for many, many values of x. Okay? So there are traditionally two viewpoints. A viewpoint which they say, I fix x and I let the flow evolve. I track the particle for all future times. Okay? And there's another viewpoint which is more well suited to fluid dynamics or continuum, the modeling of continuum media, which is to the so-called Eulerian approach, which is the following. So imagine that at t equals 0, you have a distribution on the initial condition. So it's a measure, rho, 0. It's probability measure on omega. So you have a part you're not interested in a single x, but maybe you have a probability measure, rho 0, just on this region, for instance, and each point is moving, and you're interested in how the distribution, the statistical distribution of the position of particle evolves with respect to time. Okay? And the question is, how can one characterize the measure rho t, which is the image of rho 0 by the flow? You see what I mean? It's more a statistical distribution. You have a probability distribution on the initial position. You wait for a time t, and how is this probability evolving if each particle individually is moving according to the flow? In general, this is a viewpoint which is usually referred to the Eulerian viewpoint. So, example, you can take rho 0, which is just a discrete measure, and then you let the time evolve, and at time t, this remains the image of rho 0 by the flow remains a discrete measure, but the position have moved from xi to xt of xi. Okay? Fine. So there's a remarkable property. Maybe. If you have questions, feel free to ask questions. Right? If you've never seen this before, maybe if you need more explanation, feel free to ask. Okay? So here, I'm interested, the object of interest. If you want, it's a curve of measure. Okay? So, of course, basic observation, of course, if there are some properties which I can, at time t equals 0, you see, the flow at time 0 is the identity, so of course, rho 0 is rho 0, right? Notation is consistent. So rho, you know the initial condition. What is also easy to see is that in some sense, t, the flow is continuous with respect to time. And the flow remains, I made a simplifying assumption that the flow remains in omega, right? T gives rho t is continuous. I have to explain what I mean by continuous, in the sense that if I take a continuous function, let's say, the average of this function with respect to t is continuous as a function of time. So t gives the integral of phi d rho t. Of course, it's the integral of phi xt of x, d rho 0 of x. But xt of x is continuous with respect to time. The flow is continuous. It's even smooth. Okay? So it's a curve. So you see, these are measures. If I start with Dirac masses, I remain with my Dirac masses. But as a function of time, it has automatically some continuity properties. But now the key point is that rho, or maybe I could state a proposition. T gives rho T, solves a partial differential equation, a linear one, which is really important, which is called the continuity equation, which is called the continuity equation, maybe the continuity equation, and which is the following. So the partial differential equation relates rho is a function of time and position, so it relates derivative with respect to time and derivative with respect to position. So dt rho plus divergence of rho v equals 0. I have to explain a bit. Let me recall that the divergence of a vector field, let me denote it sigma 1, sigma t. The divergence of a vector field is a trace of the Jacobian of the vector field. So it's a sum of di sigma I. And the important thing is that if everything is smooth, it's integration by parts. So it's the divergence integration by parts. Stokes theorem, if you want. Integration by parts say that, imagine that sigma and u are smooth and compactly supported, let's say. Then the integral over omega of sigma scalar product with du equals minus the divergence of sigma u. Okay? If the vector field do not vanish on the boundary, there is a boundary term, but I'm ignoring this. Is it okay?
No, then it should be boundary.
Sorry? No, I said it's compactly supported, so I ignored boundary terms.
No, in the equation.
In the equation here?
No, the last equation is indeed.
No. Okay. This is the sum of the sigma I ti u. So I integrate by part, I put the derivative here, I ignore boundary terms, so it becomes minus ti sigma I. I can do the computation, right? So here it's minus, you integrate by part each term of the sum. So you pass the i's partial derivatives here to you, and there's a sum. That's where you recognize the divergence. Okay?
So boundary. For the boundary condition, there is no boundary condition.
No, there's no boundary condition.
Because it's a separate code.
Okay. But the boundary term would be the flux of sigma multiplied by u over the boundary. But I ignore this. Right? And of course, we know that it's an evolution problem, dt rho equals something, and you know that you start from rho 0. Moreover, that's a full characterization in the sense that here I assume that V is smooth. If V is not smooth, it's a different business. What I'm going to say is smooth. But moreover, if a family of measure satisfies this equation, in a sense I will make precise in a second, and is continuous with respect to time and achieves the value rho 0 at time 0, it is the image of rho by the flow, of rho 0 by the flow. Moreover, if rho tilde t is a continuous curve, it's nice to speak about curve, right? Time-dependent function taking values in measures. I call it a curve of measure, a flow of measure, if you want. It's a continuous curve of measures, of probability measures, such that rho tilde at time equal t0 equal rho 0. What I'm saying is that there is essentially a uniqueness result. And dt rho tilde plus divergence of rho tilde v equals 0, then rho tilde t equals rho t, and rho t we know what it is. It is the image of rho 0 by the flow. So this PD, this is linear PD, V is given, this is very simple first order PD in terms of rho. It fully characterizes how an initial measure evolves when it is transported by the flow of the DOD. Is it clear? Yes.
I have a question.
Sure.
You are considering the measures with density function.
No, I'm not assuming that maybe you are shocked because rho can have direct masses or things quite nasty, and I write derivatives. Is it?
Yes, that's.
This I'm going to explain. Is it your question?
Huh?
Is your question about what is the meaning of an equation with derivatives when objects inside are just measures which are not functions? Is it your question?
Yes.
Okay, I'm going to answer it in a second.
Okay.
Of course, it's very shocking. If you are trained in PDs, you are not very. What's your name?
Alexa.
Alexa. The question of Alexa. Alexa.
Alexa.
Okay. Is it correct, Alexa? Alexa is following. Is not taking a nap during this, the course, and she said, "Well, what the hell is he doing, this French professor? Right? He writes derivatives for things which are not even functions." Okay. So I'm going to explain. That's a very good point. What is the meaning of the equation? The meaning of the equation is in the sense of distributions. My mean idea is I have to explain. Of course. Now I want to do the purpose of this course is to describe a little bit the optimal transport problem in the continuous setting. So in the continuous setting, you have to deal with derivatives, you have to deal with PDs. Of course, and the question of Alexa is a very good one. I was planning anyway to mention what it means. What does it mean? What does it mean that a curve of measures solved? Let me give a name to this equation, C, like continuity. It's called continuity equation because it captures the preservation of mass, in fact, along the flow. No mass is destroyed. It goes somewhere. It moves. So it's very natural to look for a time derivative, but the mass is moving somewhere because there is a flow, there is a velocity field, and the consistency of the fact that the mass goes somewhere and the somewhere is governed by the vector field V is captured by this PD. And of course, it's very shocking the first time you see it, because, of course, if rho is a smooth function, there's no problem about talking about derivative. Right? It means for every t and x, this expression, which is a function, is 0. But here it's not the case. The case, imagine for a moment, if rho is smooth, rho is a function of t and x, differentiable with respect to t, differentiable with respect to x, whatever you want, but it's not the case at all here. Then C has to be understood in the classical sense, pointwise. By this I mean for every t and x. But even in this case, let me do the following. Let's compute the integral between 0 and t and the integral of omega of dt rho plus divergence of rho v, which is 0, and multiply it by what is called a test function phi of t and x dx dt, where phi is what is called the test function. So it's smooth function of time and space. In fact, the integral over omega is also the integral over RD, but and here I can integrate this by part. This is minus the time derivative on rho goes on phi. Okay, it's 0t times omega of dt phi. Remember the divergence formula, Stokes formula, the integration by part. The divergence of something times phi is minus the gradient of phi times this. So there's plus, because the minus is here, rho of t and x, v of t and x, scalar product with grad phi of t and x, and there's rho outside. There's a rho here, so we put it here. Dx dt, dt dx equals 0. And now saying that, and this I can write also as the integral of dt phi plus v scalar grad phi multiplied by rho dx dt dx, and all this is 0. Okay? Now saying that the equation is satisfied in the weak sense, or in the sense of distribution, is to take this as a definition. You see here, the derivative go on the test function. Rho, so this is a smooth function, and this is a measure. You can multiply a smooth function by a measure. It's perfectly fine. So now we take this condition as a definition. This is the idea of defining a solution of PDEs in the weak sense, in the sense of distributions. So what does it mean? Rho solves C in the weak sense if and only if this identity, this quantity here, equals 0 for every phi. Okay? And this makes perfect sense. Okay? The first time you see it, the first reaction can be, oh, I'm going to hate I'm going to hate PDs. The first time you solve an equation, like a Poisson equation, it's an equation with second derivative, and you are explained that the solution is a log, you're disgusted. But after a while, you get used to this, right? Okay, so now I can prove, is it clear? So I'm saying that the way to describe how a measure is transported by the flow is totally encrypted in this equation, provided you understand it in this weak sense. Okay? Fine. Okay. I have a tiny place here where I can do the proof. Let's take phi, the test function. This is called the test function. You see, all the torture you put on rho, the partial derivatives, the operation, you put it on the test function. This is the philosophy of weak solutions. And let me compute what is in red. Compute the red. So it's the integral with respect to time and space of dt phi plus, let me write the variable, dt phi plus v of tx grad phi of tx. I was optimistic about rho t dx dt, rho t, d rho t of x dt. and maybe there's a parenthesis which is missing. But remember that rho t is xt sharp rho 0. So this you can write, it's just a change of variable. This is the same. You can write d0 0 x, d0 of x, but you have to replace x as xt of x. Okay, I'm sorry, I need more space. I need more space. I need more space. I need more space. Anyway. Okay. Let me use the blue and the red. So it's 0 t of x dt. This is the same because of this condition as the integral, the double integral in time and space, t times omega, of dt phi txt of x plus vt of xt of x, which is the flow, scalar product with d phi of t xt of x. Don't worry, after this line it's going to be finished, or maybe one extra line. But the gain is now that here I have a time-dependent measure I don't know. Here I have a fixed measure I know, dt. I can do Fubini, integrate first with respect to space and then with respect to time, or the reverse. I can integrate with respect to t inside and with respect to space outside. You see, I've never used the fact that rho 0 it's not a function, it's a measure. So here I have the integral over omega of the integral between 0 and 1, or 0 and t. I never said that t is 1. But now look, remember the ODE, the dynamics is that v is d xt over dt of x. So here you can recognize this expression, just by the chain rule, is a full derivative. This guy is d over dt of phi of t, xt of x. Yes, use the chain rule. d over dt of this guy is dt phi plus the gradient of phi multiplied by the time derivative of x, which is x dot, which is v. But you integrate in time a time derivative. So the integral which is here is just a boundary term. It's just phi of t xt of x minus phi of 0 x0 of x. x0 of x is x. Okay? But I said that phi is compactly supported. So phi vanishes at the boundary, right? It's 0 close to 0, 0 close to t. So this is 0. Okay? So this guy is 0. So I have proved that the image of rho 0 by the flow solves in the sense, in the width sense, in the sense of distribution, in the red sense, which is here. The image of rho 0 by the flow solves the PDE. Is it clear? Now, proving that it is the only one, I will not do it. It's okay. It's slightly, it's based on something called the method of characteristics, but I think it's enough of computation, right? Okay. The converse is not very, is not much more difficult, but I will skip it. Is it okay? So keep this in mind. If you want to study how a statistical distribution of initial condition is evolving when the particles are admitted by the flow of a vector field, you don't really need to track to solve the ODE for each particle and then try. No, it's equivalent to solving this equation. dt rho plus divergence of rho v equals 0. We're going to see this equation again in the future, so keep this in mind. Okay, now I'd like to illustrate this. So, okay, so it's a dynamical viewpoint on the transport process, right? We are transporting a measure, but by a flow. So it's not directly transporting mu to nu, it's transporting a measure in continuous time along the flow of a vector field. Okay, so an application. An application, you may ask yourself whether if you have two measures with nice densities, can you find a transport from the first to the second, which is a diffeomorphism? The answer is yes. And now I can answer it. So is it a theorem? Okay, maybe application, the Taconian-Moser theorem. So imagine the following. We are again in a region omega. Smooth, connected, unbounded. Imagine that on omega you have two probability densities, ρ0 or 1. Let me take them smooth up to the boundary, smooth functions, positive, larger than some a, which is positive. They are positive everywhere, but bounded from below on the wall of omega, again, up to the boundary. And of course, they have the same mass. Which you can take to be 1. So they are smooth density of probabilities on a nice domain. Okay?
Should we come back?
Yeah, I didn't. Okay, a bit more precise. Omega is smooth, bounded, and to be safe. Sorry. Yeah. I drew a picture and I didn't write the.
Okay.
Yeah, bounded, and that's it, basically. And that's it. And that's it. No, I said good. Maybe connected. Yes, because it's not connected, maybe the different connected components do not have the same mass. So, of course, yeah, I need connected. Just to be safe. So here is the theorem. In this setting, there exists T, which is a C infinity diffeomorphism, such that T transports ρ0 to ρ1. Okay? Like this as a long history. It was first done by Moser in the 60s. But he was not really addressing, it was dealing with volume forms on manifolds without boundaries, to deal with boundaries. We worked on this in the 90s with Bernard Lacroix and end up with this theorem, which I think is very nice. I can prove this. Proof. So proof goes like this. So let me introduce rho t of x, which is 1 minus t rho 0 of x plus t rho 1 of x. So it's called Moser's deformation argument. In fact, I don't need really this one, but I deform one measure onto the other. by a parameter t between 0 and 1. It is smooth, and it is away from 0. It's larger than a, which is strictly positive, right? Larger than a, it's strictly positive. So also 1 over rho t is a smooth function. And d t rho is, of course, rho 1 minus rho 0. Now here is the trick. If I can solve dt rho plus divergence of rho v equals 0, but with this rho, and I cook up a v which does the job, I'm done. That's the idea of the coordinate model. In fact, they did much more in their paper, but I don't want to go into this. It's a beautiful paper. So now, okay, let us solve. Here, I have to ask you to believe me, but it's a standard result, that you can solve the following equation. The Laplacian of u, the Laplacian is the sum of the pure second derivative, so it's the divergence of the gradient, equals rho 0 minus rho 1 in omega with du over dn. So du over dn is the scalar product of the gradient with n equals 0. Because the right-hand side has total mass 0, in fact, you can solve this equation, and its solution is smooth. Okay? That's something you learn in PDs. This is the unique, well, up to a constant, because u is defined up to a constant, solution up to constant u, which is smooth. Okay? The Laplace equation is quite nice. Smooth data, you have a smooth solution. Now define the vector field Vt. Let Vt of x be the gradient of u of x divided by rho t of x. Well, this is smooth. This is smooth. It doesn't vanish. It is smooth. Also, Vtx, if you are on the boundary, the vector field is tangential. Here, this means that the gradient of the solution lives in the tangent space. Equals 0. So, okay. So exactly in the framework I studied before. And now let's compute dt rho t of x. Now, Alexa. Now, Alexa, we are in the smooth case. We are not considering a generalized solution. It's a smooth function of everything. Plus divergence of rho v. Look, dt rho is rho 1 minus rho 0. V is grad u divided by rho. So the rho cancels out. So it gives me divergence of gradient of u, which is the Laplacian of u. And the Laplacian of u is rho 0 minus rho 1. So it is 0. So this deformation, this pass from rho 0 to rho 1, which is the simplest one, right? It's a linear deformation, convex combination, right? Is induced by a vector field. So, if you look at the flow of the vector field, so if one defines this, then, and the flow is smooth diffeomorphism, right? Then rho t, which is 1 minus t rho 0 plus t rho 1 is xt sharp rho 0. And in particular, it is true for t equal 1. This is for every t. In particular, it's true for every t between 0 and 1. So for t equals 1, I discovered that rho 1 is x1 push forward to 0. But this is a smooth diffeomorphism. Okay? So if you have smooth, okay? Is it clear? Okay. So I think it's enough of examples of transport maps, but you see, I've given you an idea of several techniques, PD techniques. There is a monotone rearrangement, which is very classical, on how to build transport map between measures with nice densities, right? If measures are arbitrary, by matrices and so on, of course you cannot do that. Okay. You have questions? No? Okay, so now let's play another game. Let's play another game, because if we will solve at some point some instances of the Monge problem, it's just too difficult. So we have to make some detours, and the detour is through the so-called Kantorovich description of the mass transport law, which I believe is more or less what Jean Bernard has described in his course, right? But in the finite setting, right? Now comes the Kantorovich or Monge-Kantorovich, the Monge-Kantorovich formulation. Formulation of the OT, optimal transport law. So again, to give you an idea, they're jumping in time. So it's the work of Leonid Vasily Kantorovich, the famous Soviet mathematician, who introduced this problem, studied at the time of World War II, around 41, 42, which, as you know, was quite a tough time for Russia, because Kantorovich was a mathematician. He was in Leningrad, but the Nazi army was making the siege of Moscow, of course, but also in Leningrad. So they were stuck in the major Soviet cities, trying to launch some counterattacks to overcome the turning point of the World War II. And Kantorovich thought of the following problem. Well, he called it transshipment, or the allocation of masses problem. So imagine the following. Imagine that you have a bunch of mines. You have mines. Okay. I'm going to denote them by circles. And there are steel factories. Okay. And the problem is how to efficiently transport the coal from the mines to the factories. And it was a serious problem at the time, right? To make the Soviet army powerful again, you needed the transport process and the plants and so on to run forever, night and day, right? Otherwise, people would have, well, actually the situation was dramatic in these cities in 41, 42. So coal mines, and there are steel factories, which I'm going to denote by triangles. So I think there are here. And there are some, and of course, the demand is more or less here. So think of Leningrad, think of Moscow, or Moscow being slightly here, slightly there. Okay, something like this, or maybe there is also something. Let me describe it in discrete first. So the coal mines, we have location, so there are n of them. Here there are j, there are m of them, or yeah, I and j is better. I, j, okay. And they are located at points xi, locations xi, and the production of mine xi is denoted mu I. Okay, production. Okay. Here, the location is denoted yj, and the demand. Okay, you have to again. It's not a joke. Kantorovich was not working on it just for fun, right? He had strong incentives by the Soviet government to seriously think on how to plan efficiently the production, the transport of the. Okay, and there's a demand mu g, and of course there is a compatibility condition. Compatibility condition, which is the sum, the total supply equals the total demand. Maybe it's not one, but it's a common number. So now you immediately, and of course you can think these are just points, but think of this mine very far from it, but the production is huge. And maybe the production here is pretty small, and you obviously see that the number of mines and the number of factories may be not the same. So it is clear that what is given is there is a transport cost Cij, which is the cost of transporting 1 unit, the cost of transporting 1 ton, transporting 1 unit of coal from xi to yj. This is given. This is given, and the unknown are what Kantorovich introduced, which is the notion of a transport plan. You see, you start from this coal mine I, or maybe 1. Maybe it's transporting, maybe it sends some product. Imagine that the production is huge here. Probably it dispatches some here, some there, some there, some here. Maybe it's too costly to go there. Maybe this one would be better receiving thing from here or from there. But what you see immediately, maybe this goes here, maybe this goes there, maybe a little bit of this goes there as well. Maybe this sends a bit here and a bit there, maybe a bit here, a bit there, and a bit there. So you see that a single mine may send some coal from different factories, and a given factory may receive coal from different mines. So don't think about Monge maps anymore, right? The Monge world is very rigid. What is produced at X is to be sent to a destination T of X. No way to say I'm sending 1 part to Moscow and 1 part to to Leningrad. At the time, St. Petersburg was called Leningrad, as you know. Okay. So the unknown in the Kantorovich problem, the unknown in the Kantorovich problem is what he called the transport plan, very much in line with the Soviet organization, planned system, planned economy. The unknown is a transport plan. So it's a matrix, if you want, gamma ij. And gamma ij is a mass sent from I to j. Okay? Makes sense. This captures a little bit the drawing, which is the board on the left. So what are the feasibility constraints? Feasibility of a transport plan. Or transference plan. When you look at a given mind, I, and we saw, first of all, gamma ij's would be non-negative, right? You do not destroy coal. You really need the coal to build the planes, weapons, and so on to prepare the counterattack. There's also a funny story about Kantorowicz. He was really asked to. He was young at the time. I forgot to say that Kantorowicz was probably the only Soviet mathematician who received the Nobel Prize in Economics in '76, because more or less he invented. Maybe I don't know if Jean-Bernard agrees. He really invented two important things: duality for linear programming, independently from what was done in the West, and prior to what was done in the West, probably. And invented decentralization by prices. Okay, so, but also he was asked at some point to think to there's a lake around Leningrad or St. Petersburg, which is typically frozen during the winter, and there was the idea: could it be a good strategy to have trucks providing some goods, some food, and so on, to the city using the lake? But of course, if there are too many trucks with a certain frequency and so on, it's dangerous. So he computed, made some sort of, he solved an optimization problem, advising which frequency the trucks should ride on the frozen lake. But it didn't work because all the trucks were destroyed by the planes of the Nazis, the Nazi army. Okay. So, okay. So transport plan is a description on how you plan what is sent to where. So what are the natural constraints? The natural constraints is that if you fix an I, the sum of a j should be what is produced in the mind, which is mu I. And likewise, for every j, if you sum over I, gamma ij, this is what is received by factor ij, which is its demand, ug. This is mass conservation. Okay? So this is 1, this is 2. These are called marginal constraints. I'm going to describe it more in details later. And the Kantorowicz problem, which is a typical problem of linear programming, which is minimize the sum of the Cij gamma ij, subject to non-negativity of the Planck, and 1 and 2. Okay, this is linear programming. It's clear that the solution exists because the admissible set is non-empty and is compact. Okay, so it's clear that the solution exists. Okay, fine. Now, what is nice with this formulation is that, of course, it can be generalized. Here, you don't need maybe a more precise modeling would lead you to model the distribution of mines and the factories incorporating general measures, not necessarily discrete ones. So let me describe the general form of Moszkotowicz. Try this one. The general form general form. I consider general spaces, X and Y, but maybe not so general, let's say compact metric, just to make things simple. Compact if you want, metric. You got mu in P of X. This is my distribution of mines. Nu in P of Y, my distribution of factories. You got cost, let's say continuous on X times Y. This is my transportation cost. In the discrete case, it's just a matrix. Now I need the notion of a transport plan and then the notion of margin. So I need two definitions. Definition one. So the idea, before definition one, let me give the idea. The idea, describe transport in the spirit of Kantorowicz by a measure gamma on the product space plan, if you want a transport plan. And what does it mean? It means that gamma of A times B, imagine that A is a measurable subset of X, that B is a measurable subset of Y. Gamma of A of B is the mass transported from A to B. Of course, in the picture here, there's X and Y are just finite sets, so you just have to identify how much amount of mass is sent from I to J, from a point to another. So to capture mass conservation, so I have to introduce a definition. Marginals. So let's take a probability measure on the product space. Okay. The first marginal of gamma, denoted pi x. In fact, it's a notion we have already seen, right? If you have a product space, you can define the canonical projections by x on the first factor and by y on the second factor. These are the canonical projections. Is the probability measure on x defined by pi x, first marginal pi x sharp gamma of a set A is gamma of A times the full second space for every A included in X of X. This is the same, okay? This is the same as saying as for every continuous function on X, if X is compact, I don't have to be precise about spaces of continuous function. They're automatically bounded and so on. The integral on X of phi times its first marginal is the integral of the product space of phi of X d gamma of xy, right? You just integrate a function of one variable with respect to the two variables. Is it clear this definition? Or? Now I can define the second marginal of gamma, denoted pi y gamma, is the probability measure on y, defined by pi y gamma of a set B, but now the set B will be a subset of y, will be the mass of X times B for every B in Y over N. And if you don't like to define it this way, you can define it with test functions. For every psi continuous in Y, the integral on Y of psi d pi x of gamma is simply the integral psi of Y d gamma of xy. Is it okay? So for instance, to make things simple, the marginal, imagine that you are on R2. Imagine that you have a measure mu with a density f of x1 and x2. The first marginal is just, it has a density which is the integral of the density with respect to the x2 variable. Okay? Just use this formula. This is what I have used when I described the triangular transport. Remember? Okay. Maybe a remark? Imagine that you have a random vector x1, x2, which has a distribution gamma. And x1 follows the first marginal, well, I1, change its notation, and x2 follows by2 of gamma, right? Random vector. Now, definition 2, which is related to when is a plan gamma or probability measure of x times y compatible with mu and u, or measure preserving. It's a notion of a transport plan. So gamma in P of xy, x times y, sorry, is a transport plan between mu and u, if and only if the first marginal or mu or gamma, sorry, is mu and the second marginal of gamma is nu. Again, if mu and nu are discrete, this is exactly the kind of gamma is just a matrix, and the constraints on the matrix is that the sum on rows and the sum of columns is fixed. This is exactly as in the problem of contouring, the discrete problem of contouring. And one denotes by pi of mu nu the set of transport plans. Sometimes it's also called couplings. A coupling or a plan. Coupling or a plan. In probability, we prefer to talk about couplings. In analysis or mass transport, in general, we prefer to talk about plan. It's a set of transport plans between mu and u. Okay? And now what is the Monge-Kantorovich problem? And the Monge-Kantorovich problem then is as follows. It's to minimize. So let me call it MK. Kantorovich was aware of the work of Monge, and the Monge studied. I mentioned the connection between both problems. It's minimize the total cost, so it's the average of C against gamma, subject to the constraints that gamma belongs to P of mu nu. Okay? Makes sense. You have marginals, mu and u, which are fixed, and you look for coupling, and coupling, as I explained in the discrete case, is linked to preservation of mass, fixed marginals, and among these physical couplings, you try to make the average transport cost minimum. Okay? So, now, let me make a bunch of remarks, but maybe a theorem is better than a bunch of remarks. When I introduced Monge problem, I immediately said, ooh la la, the problem is difficult. First of all, the physical set is empty, maybe empty. If it's not empty, I gave an example where there is no solution and so on. So it's not to be scary, but here the problem is much better behaved. First of all, you can notice that it is linear, right? The integral of C d gamma is linear in gamma. You can notice, maybe, yeah, let me make some remarks. I said I wouldn't do remarks, but I cannot help doing remarks. The first remark is about non-emptiness of pi of mu nu. Remark. Define what is the usual probabilistic definition of a tensor product, right? It's the independent coupling. For every test function of x and y, the independent coupling, d mu tends to nu of xy, is just the integral of phi xy, d mu x, d mu y on the product. In terms of random variables, it means that the first component is drawn according to mu, the second component is drawn according to nu, but they are independent. Maybe having something independent is not clever in terms of optimization, but it's feasible. So you will see, this is called the independent coupling. And you see that this is always, if you integrate a function of phi, if you integrate a function of x only, that's the integral of phi of x, d mu x, integral of d mu y, which is 1, so it's the integral of phi of x, d mu x. The first marginal is mu, and by the same computation, the second marginal is nu. So the independent coupling is a coupling. So pi of mu nu is never empty. Okay, it's not a matter of atoms and whatever. Here, it's always non-empty. Okay. Now let me state the theorem. Theorem. MK admits solutions. Okay. Here I don't recall the framework, but I assume that X and Y are compact and that C is continuous, for instance. So what do we need? We need to find a topology. Of course, it was a total failure, as I tried to explain last time, in the case of Monge. Okay? Either we're using some kind of strong topology, but then we had sequences of maps which are not strongly compact, or we use weak topologies, but the constraint is not stable by the very weak topology. So we did. So okay, let me prove this theorem. Proof. So probably I should say the following. I should say that I should endow a set P of xy with so-called the weak star topology or convergent, convergent. To enter subtleties. So what does it mean? What is the weak star topology of a set of probability measures? Where I'm going to say that gamma n weakly star converges to gamma if and only if the integral of phi d gamma n converges to the integral of phi d gamma for every phi, which is continuous. So it's just the topology generated by integrals of continuous functions. Okay. So an important fact is that P of xy is compact for this topology. Okay. So each time you have a sequence of probability measures on a compact set, you can find a subsequence that converges for this mode of topology, for this mode of convergence. Okay. This comes from the fact that measures form the dual of continuous functions, and the probability are in the unit ball of the dual, and the unit ball of the dual is always compact for the weak star topology. But I'm not working on P on xy. I'm working on a smaller set. So now consider gamma n Now I'm saying that pi of mu nu, we have just seen that it is non-empty. If I show that it is weakly star closed, when it's a weakly star closed of a compact set, it's compact. Again, for its topology. But okay, so we have just seen. We have just seen that pi of mu nu is non-empty. It contains the independent coupling. It shows that it's closed. So let's take gamma n in pi of mu nu. Assume that gamma n converges for its topology to some gamma, and I have to show that this gamma has marginal mu nu. So let's take a function of x, a continuous function of x. The integral of phi gamma n xy is the integral of phi d mu, because gamma n is first marginal mu. but a continuous function of x is a continuous function of x and y. It just does not depend on y. So by weak star convergence of gamma into gamma, this converges to the integral of phi d gamma. X dxy. So this guy equals this guy. And phi is arbitrary. So it means that the first marginal of gamma is mu. The set of probability measures which prescribe first marginal mu is weak star closed. It's the same. The same for the second marginal. You just take a continuous function of y, you arrive at the same thing. Same for the second marginal. That's so py of gamma, the second marginal is mu. So pi of mu being closed is in fact compact. So now I'm optimizing the function of a compact set, non-empty. I just have to check that what I minimize is continuous, or Laurent semi-continuous, but in fact it's continuous. But look, C is continuous. And the weak star topology is precisely made on purpose to make gamma integral of C d gamma continuous for the weak star topology. By definition. The weak star topology is you just take phi equals C. Okay, to existence of the minimizer follows. Okay. So now you may ask yourself something. I started with something I claimed quite quickly super hard. And now I describe another problem, and after a few seconds, we got an existence theorem. So we should discuss a little bit what is the connection between the two problems, right? And of course, here I simplify my life a lot. As you may guess, you can replace C continuous by C Laurent continuous. You can replace compact metric spaces by much more general ones. It's okay. Plenty of things you can do. But the main thing is that here, automatically, there are transform plans. It's automatic. So comparison and differences with Monge. Connections differences with Monge. Here in the Monge-Kantorovich problem, the viewpoint is not the same. In Monge problem, there is this idea of that all the mass, I think I said it already, that all the mass which is at x is sent to the same destination. There's some sort of a deterministic process, right? You look for a map. The mass which is at x is sent to Tx. That's too rigid, okay? The description of Kantorovich is much softer, right? The mass which is of x can be sent to several destinations. So maybe to understand this, I should state a theorem, which is folklore, but to explain the difference. So, in a nutshell, Monge. So let me write Monge here. It's infimum of the integral C of x, T of x, T of x. With the constraint that T short mu equal nu, it deals with maps. And Monge-Kantorovich, it deals with plans. And in fact, now I know I have proved that the infimum is achieved. So let me write it as a No, it's me. Gamma in pi of mu. Maybe to understand the difference, let me draw a picture. Put X and Y here. In Moore's world, okay, the mass which is here, so you have a distribution of mass mu here, you got a distribution of mass mu there, but in fact, you should maybe it's discontinuous, but you're looking for a map, right? Maybe it has discontinuities, maybe it's wild, but for sure, X is tend to T of X. No mass except all the mass which is at X is tend to T of X. No mass, there is no other point than T of X which receives mass from X. This is the world of motion. This with maps. Whereas in the world of Kantorovich, it's totally different story, right? You have a distribution here, a distribution there, but on top of X, there is also a distribution. You can send some mass here, some mass there, and maybe you can have some distribution. The mass which is at X is sent, there's a distribution of mass on Y, which depend on X. So this is related to the so-called disintegration theorem. Or maybe if you've seen in probability theory, it's just the notion of conditional probability. Theorem. If gamma has first marginal mu, first marginal mu, then you can say that there exists a family indexed by X of probability measures. You can think of conditional probabilities on Y, such that gamma is a tensor product of mu with gamma X, which is just a notation to say that when you take the average with respect to gamma, in probability it's called the tower property. The expectation is the expectation of the conditional expectation. The integral of function of two variables is you can first integrate outside, you integrate in the X variable, it's the expectation in the X variable of the conditional expectation in the Y variable given X. And this is called the disintegration. So, okay? So if X1, X2 is a random vector with low gamma, X2 given X1 equal X has low gamma X. That's what I'm saying. So you see here, the distribution which is here is gamma X. If you look at another point, X prime, it's another distribution, gamma X prime. So what you're saying, it allows for mass splitting. Huh? Very soft. Mosh is very rigid. Higgs, the mass which is here, is sent to T of X. The mass which is at X prime is sent to T of X prime. So here, it means somehow that the only disintegration you allow is a Dirac mass. Okay, you see here I just this is Monge. No way to send the mass at X to anything else than a point. In Monge-Kantorovich, maybe some points are sent to points, but maybe other points are sent to distributions. Okay? Okay. Now, just to finish, I'd like to make two comments, or maybe to make a comparison. For T, a map. I can define a product measure, define gamma T by mu tensor delta T of X. What do I mean? I mean that the integral of a function of two variables against gamma T is just the integral of phi. So you see, it's a measure whose first marginal is mu and which is supported by the graph of the map T. X, T of X, d mu of X. You can observe that the first marginal of gamma T, if you take just a function of X, you got the integral of phi of X, d mu of X. So the first marginal is always mu. And what is the second marginal of a guy like this? A second marginal, if you take just a function of y, the integral of phi of y d gamma T of xy is the integral of phi of T of X d mu of X. That's T sharp mu. That's the definition of T sharp. So, gamma T is a transport plan if and only if its first marginal is mu, but it is already true. And its second marginal is mu, which is true exactly when T is a transport. Moreover, the integral of C of X, T of X, d mu of X, what you optimize in the Monge problem is by definition the integral of C of xy, d gamma T of xy. So you see that Monge is exactly the same as Monge-Kantorovich, but when you restrict yourselves to plans which are of the form gamma T, maps which are plans which are sparse, which are given by a map. So, two things, consequence. So, first of all, the infimum of Monge is larger than the minimum of Monge-Kantorovich. Why? Because everything you can do in the Monge problem, you can use a T in the Monge-Kantorovich. So each time you have a transport, what it costs is certainly larger than the minimum of Monge-Kantorovich. At this. 2. Okay? This is a relaxation. So Monge-Kantorovich is a relaxation of Monge. But the second observation, of course, you may ask yourself whether the relaxation is exact. If there is a huge gap between the two problems. Of course, what I'm saying is that in Monge-Kantorovich, you optimize over a larger set than in Monge, but you basically minimize the same thing. Just Monge is Monge-Kantorovich restricted to sparse couplings, which are couplings given by maps T. But if we are lucky, and find, and in fact we will see that it happens, and find, in some cases, and find a solution of MK, which for some reason is of the form gamma T. If it's a form gamma T, then T is a transport, and this cost is the minimal cost, and then it solves the Monge problem. So it's a new strategy. It's a relaxation, solves the Monge problem. So if we are Now we have a relaxed problem introduced by Kantorowicz. Maybe we like it better because it's more suited to describe transport from mines to factories, for instance. So it's less rigid than the old-fashioned description of Monge. And on top of that, if we find good tools to study the Monge-Kantorowicz problem, which enable us to find situations in which the optimal gamma is in fact concentrated on the graph of function t, then we have solved the hard problem. Okay, this is just to hopefully give you incentives to come next week. Okay, thanks. I'm gonna stop here today. Okay. Questions?
I imagine that there are some like conditions that you can put for the problems to be equivalent.
Yeah. Of course, I will discuss this.
Okay.
Sure. I start again from this point, right?
Yes.
Okay. Oh, of course.
Okay.
Merci.
Il est encore.
Yo te paso mis notas. Pero mi causa ya me dijo
Je peux te laisser mon sac.
Sí, ¿cómo se dieron cuenta? No sé. Tu cara de nervioso, dijo, no, yo no sé.
No, pero yo pensé que.
De verdad que quiero. Yo mi correo universitario tengo. No, me olvidé de recogerlo.
Claro, la salida tiene que estar acá.
sexual restriction, some of the tries a long time, behavior, crucial questions, objective features, they are also questions. And the situation are also very influenced from structure to content. So they say, being a grateful movement, some important to be given this space, and this space is fastest. So it's for instance,